Let's see if we can use the idea of implicit derivatives to find a derivative formula for the slope at any point on a circle. A circle is definitely not a function. The only way that we can write a circle in a single expression is to write an implicit equation, that is, an equation that we cannot rearrange so that we have y to the first power by itself on one side. We can do that with a circle, but we have to break it up into two pieces. We can have y equal to positive square root of some expression, that'll be the upper half of the circle, and y is equal to negative square root of some expression, that's the bottom half of the circle, and that gives us two functions. But a circle isn't a function, so it's a great candidate for the idea of implicit derivatives because the only way we can really write it is implicitly. So let's take the derivative term by term on both sides. We already know the derivative of x squared with respect to x is going to be 2x. We could think of there as having a dx next to it. But we have the same thing top and bottom, so that's really just a big 1. So we don't need to write that down. But when we take the derivative of y squared, that's going to be 2y. But it is going to be multiplied by dy dx. Now that's not the same thing top and bottom. That's an important thing for us to keep track of. In this case, that's going to be equal to 0. If we subtract 2x from both sides, we get 2y times dy dx is equal to negative 2x. And if we divide both sides by 2y, we end up with dy dx is equal to negative x over y. Try it out. See what you think. Some good values to try are the left and right, or I should say leftmost and rightmost points on the circle. Those are places where we expect to get an undefined slope because we have vertical tangent lines. Also try the topmost and bottommost points on the circle. We expect to get horizontal tangent lines there. This formula should go to 0 when we do that. I also just want to take a brief moment to note that essentially what we do is we take the derivative implicitly. Anytime we take the derivative of something involving y, we pick up a dy dx. And we end up with a formula where dy dx is kind of embedded in it. And there may be more than one dy dx embedded in the formula. So our next step is to try to get the dy dx pieces by themselves. If there are multiple ones, then we'll factor the dy dx out. If there's just a single one, we'll divide. If we have to factor out, once we get down to just a single dy dx times some expression, then once again we can divide. So we're going to go through the same set of steps. They may be less or more complicated depending on the problem, but take the implicit derivative first, get all the terms with dy dx on one side, any terms that don't have dy dx on the other side of the equal sign, factor a dy dx out if you need to, and then finally divide so that we get to 1 dy dx. It will be equal to something that will involve both x and y typically with an implicit derivative. That's just something that happens. And since we can't in this case write y explicitly, we're stuck with this formula. But the important thing in the implicit derivative is that we have the dy dx by itself on one side.